parametric coordinates. Basically, it's a different way of describing graphs. We're used to using what's called Cartesian form. You may have even heard it called the Cartesian number plane. And what we're used to doing is our graph described by one equation, and then we have a set of coordinates. A point is described by two numbers. Parametric coordinates sort of flips that idea, where the curve is now represented by two equations, one for the x value, one for the y value, and then the point is described by one number, which then links those two equations together. And that number is called the parameter. So let's look at our parabola, which we know in Cartesian form is y equals x squared. So that's our Cartesian equation. This is an example of a parametric equation. You can come up with different ones, but that particular parametric equation would describe the same curve. So the x value is described by t divided by 2, and the y value is described by t squared on 4. So a point like minus 1, 1, well, they're the Cartesian coordinates. Parametrically would be represented by the single number negative 2, because if you substitute that into the parametric equations, you can see we come up with the same coordinates. The x is negative 2 on 2, negative 1, and the y would be negative 2 squared, which is 4, 4 on 4, 1. So we come up with the same point and the same curve, it's just a different way of doing it. So t is known as the parameter, so negative 2 is the parameter at that point. There's minus a half a quarter, its parameter would be negative 1. The origin, 0, 0, amazingly, the parameter is 0. Then there's half a quarter, that's t equals 1, and 1, 1, that would be t equals 2. Okay, so how do you change from one to the other? If they've given us these parametric equations, how do we work out what the curve is? So you're going to have x equals some function of t, you have y as some function of t. They're our parametric equations. You basically want to get rid of the t. We're not used to seeing the t, so we want to get rid of it. It's like simultaneous equations. So just say we've got x equals 2t plus 1 and y equals 3t minus 2. That wants to show that this actually is a straight line. Well, if I rearrange x and make t the subject, and so I get half of x minus 1, but now I'll go and substitute in to the y. So I get rid of the t, I eliminate it. And what I'm left with, once I play around with the algebra, I get something that I recognise to be the equation of a straight line. So I say, very much like the substitution method in simultaneous equations. How about this one? Sometimes it's not immediately obvious how you're going to do it, because we've got x equals 2 plus cos theta, y equals 1 plus sine theta. How on earth do I make theta the subject of one of these? Oh, I heard someone say it. You're right, we're going to use trig identities. So I'm going to use this fact. We'll look at this again when we do look at trig in more detail in our next topic. But you might recall that sine squared plus cos squared is always equal to 1. Do you call that identity? That's what we're going to make use of here. So instead of making theta the subject of the first one, I'm going to make cos theta the subject. So cos theta is x minus 2. And in the second one, instead of making theta the subject, I'll make sine theta the subject. And now I'll substitute into sine squared plus cos squared is equal to 1. This is a fact that I know. And I end up with an equation which I now recognise. I've got a circle. And the origin's been moved to 2, 1, and the radius is 1. This one's a little bit more involved. So we're actually going to draw up a table of values. Because sometimes when you look at it and you're not sure, there's nothing wrong with going back to, well, what is it, a year 7 idea. Plot some points. Have a look at the picture, see what it ends up looking like. So that's what I'm going to do here. X is sine theta, y is sine 2 theta, and we're going to use the, well, multiples of 30 basically, isn't it? So there it is, I've already filled it out. Going from 0 up to 360, there's all our x and y values. Let's plot them. There's the easy one. Then I'll keep going. Whoop, there's the next one. Whoop. Oh, next one. All right. What on earth is that curve? Well, you'd be looking at that and going, I've still got no idea what that looks like. So maybe you would plot some more points to get a bigger picture. But actually, there it is. Ooh, that actually is the curve right there. What is its Cartesian equation? We have what's known double angle formulas. Some of you may have seen those before, I'm not sure. But sine 2 theta is 2 sine theta cos theta. If I draw myself up a little triangle and theta, well, sine theta is x on 1. So opposite over hypotenuse is x on 1. Bit of Pythagoras, the other side's the square root of 1 minus x squared. So now I can work out that cosine theta must be the square root of 1 minus x squared. So I end up with y equals 2x times the square root of 1 minus x squared. Sort of. It actually ends up being y squared is 4x squared, 1 minus x squared. You see, the first one only gives me half of the picture, but I got that reflection above and below. Remember when we looked at square root graphs? That's what we made it y squared equals. I just thought it was a nice illustration of something in parametric coordinates. Get something a bit unusual, something we haven't seen before. There's our parametrics 5H.